Hello. Now we're going to talk about acids and bases. Um, so first up is acids. Acids are proton donors. So they donate that hydrogen proton or hydrogen cation. They have a pH lower than 7, so it's from 0 to 7. They taste sour. They turn blue litmus paper red, and methyl orange will turn red when it is in contact with an acid. Acids react with active metals to produce H2. They react with carbonates, and they neutralize bases. Acids are proton donors, so basically if you see a compound with H or H2 in front of it as like the first thing, then it is pretty good guess that it's an acid. Strong acids are assumed to be 100% ionized in solution, meaning they are really good at separating into their ions and donating that H plus cation. Weak acids are usually less ionized in solution, so they're not good donors, and they'll generally hang on to those hydrogens as opposed to the strong acids. Again, acids have a pH less than 7, so we're going to be looking at this range right here. So we've got battery acid, lemon juice, gastric fluid, carbonated beverages, sodas, vinegar, orange juice, all that good stuff. Pure rain is actually below 7, so it's acidic anyway. And then freshly distilled water is on that 7 mark. That's the neutral mark. Acids affect indicators. So if we have blue litmus paper, it's going to turn red when an acid hits it. Methyl orange will also turn red if there is acid. Acids react with active metals. So if we have a metal and an acid, we're going to form a salt and hydrogen gas. So the proton right here is going to react with the anion right here, the cation is going to form with the anion right there, and then this H2 will separate off into a gas. And that's true with every single one. Acids react with carbonates. So this is our acid right here. This is our carbonate, and we're going to get that sodium acetate thing, water, and carbon dioxide. Effects of acid rain on marble. So calcium carbonate, so this is like acid rain hitting marble statues or calcium carbonate, same thing. We're going to get a decomposition of that marble to form these compounds, except calcium will be right here. Acids are going to neutralize bases, so if we have an acid and a base together, if we have an acid and a base together, so this is your acid, this is your base, we're going to form a salt and water every single time. Water, salt, water, salt. Now looking at properties of bases. Bases are proton acceptors, so they're going to accept that H plus cation. So in that case, they are generally like something like NaO minus, and it needs that H plus ion to form NaOH. Bases have a pH greater than 7, so anything above 7 is a base. They taste bitter. They affect indicators. The red litmus paper will turn blue, and phenolphthalein turns pink purplish. Bases feel slippery, and then they also neutralize acids. So that NaOH that we used in the lab on Tuesday, that NaOH was actually slippery if you felt it, because it is a base. They accept that proton, that H plus ion, so, Nope, nope, nope. So all of these hydrogens right here are because this part accepted that hydrogen. Hydroxide, which is OH, is in a base, combines with H plus in acids to form water, and that is how it neutralizes. Bases have a pH greater than 7, so if we look on the bottom of this chart, we've got anything in this range is a base. Household bleach, ammonia, baking soda, seawater, blood, milk of magnesia, those are all bases. Soap is on there. This is how it'll look. So that's red litmus paper, and it turns blue when it touches a base, and then the phenolphthalein will look like that pinkish purple when a base is indicated. Bases neutralize acids. Milk of magnesia contains magnesium hydroxide, MgOH2. We know it's a base because it says OH, which neutralizes stomach acid, HCl, to form a magnesium chloride and water. Strong acids and strong bases, when they come together, the net ionic equation is just that H plus and hydroxide ions to form water. If we have a weak acid and a strong base, the net ionic equation contains the OH and the weak acid producing water and the ion of the acid. So the anion of that part. So for example, acetic acid reacts with potassium hydroxide. This is the net ionic equation. It does not contain the potassium anywhere in the equation, but it does contain that weak acid in the net ionic. Acid-base titration, so we're going to have a solution, either an acid or a base, and then it's going to be in the burette, and we're going to slowly let it drip down into the Erlenmeyer flask. The concentration of one of those things will be known, but the other one is unknown, and we're trying to figure out what that concentration is using the equivalence point. So the equivalence point is when the moles of acid are going to equal the moles of base, and if we know the moles of both of those, and we know the concentration of one of them, we can use our M1V1 equals M2V2 to figure out the concentration of the other one. We use an indicator to signal when that equivalence point happens. Usually it turns a certain color when the pH changes. So for phenolphthalein, when the equivalence point occurs, you will see it turn pink, and it'll be very, very light pink at that equivalence point. If you go past it, then it's a bright pink. So the goal is to be like very, very light pink, and it stays. So optimally, the indicator would change colors at the equivalence point, but realistically, the equivalence point isn't generally pH of 7. But we can kind of figure where it will be. The endpoint is the point of indicator color change, which closely approximates the equivalence point. I think this is a pretty cool chart. We can see these different indicators and where they change their color based on pH. So we use phenolphthalein a lot. We use phenolphthalein a lot. And at the equivalence point, we are on this one right here. And it changes color at around 9 pH. And you can see like the different ones and the color change that will occur. We can use a pH meter, which we will, to plot the titration curve. The equivalence point is the most vertical part of that curve, and it'll look like this. At the very, very top, most vertical point is the equivalence point, and that is where our color change will occur. And we will be doing these titration curves in our labs. So here's an example So what volume of 0.1 molar HCl solution is needed to neutralize 25 milliliters of 0.35 molar NaOH? So the net ionic equation is a strong acid and a strong base, so our net ionic equation is just our ions to yield water. We need to find the moles of the reactant, OH minus. So we do the moles equals molar times the liters, 0.35 molar times 0.25 liters equals 0.00875 moles of OH minus. We need to find the moles of H plus by just doing a mole ratio, which is just 1 to 1. And then we can find the the volume of HCl because we have the moles of H plus and we have the molarity of the HCl, that we can find the liters that were used. A student carries out an experiment to standardize a sodium hydroxide solution. To do this, the student weighs out 1.3009 gram sample of potassium hydrogen phthalate, which has a molar mass of 204.22, has 1 acidic hydrogen. The student dissolves the KHP in distilled water, adds phenolphthalein as an indicator, and titrates the resulting solution with the sodium hydroxide solution to the endpoint. The difference between the final and the initial burette readings indicate that 41.20 milliliters of the NaOH solution is required to react exactly with the 1.3009 grams of KHP. It says calculate the concentration of the NaOH, which is what you will be doing in titration experiments. So, first thing they do is write the balanced net ionic equation. Then they find the moles of KHP. They're given the grams. They have the molar mass. They can find moles very easily. Moles of OH required, it's a 1 to 1 ratio, so it's the exact same. And the molarity of the NaOH, we use the moles of NaOH over the liters, and we get the molarity. And that's the concentration. Here's another example. An environmental chemist analyzed the effluent, the released waste material from an industrial process known to produce the compounds carbon tetrachloride and benzoic acid, a weak acid that has 1 acidic hydrogen atom per molecule. A sample of this effluent weighing 0.3518 grams was shaken with water, and the resulting aqueous solution required 10.59 milliliters of 0.1546 molar NaOH for neutralization. Calculate the mass percent of the benzoic acid in the original sample. So we wrote out the equation. The molarity is moles per liter, which is 0.1546. They told us that in the equation for NaOH. And that's going to equal X over 0.01059 liters. So we're finding the moles of NaOH. And then using the moles of NaOH, we find the moles of the benzoic acid, and then we can use the molar mass to find the grams of benzoic acid. Mass percent, we're looking at the grams of benzoic acid over the grams of the whole thing, times by 100, and we get 56.77% of that effluent was benzoic acid. And that is it. So we'll be doing a lot of titration stuff. So this stuff is very important. Knowing these graphs is very important. And then you will have some stuff like this, but I think it is a little bit easier than the titration stuff. All right, and that is it.